So we come back to spanning tree. Basically, spanning tree, what it does is it makes a tree out of any graph. You can connect the way any way you want, and the computers or the switches will automatically figure out which links should be disconnected to make it a tree. And the way it works is that they select a root, and root is the one which has the lowest priority and the lowest, so it's not really called priority because priority means, just the opposite. So which has the lowest priority and the lowest MAC address in that priority. So every bridge, every switch is administratively assigned a priority. So the manager sets the priority into the bridge, that your priority for beginning the route is such and such. Or it might be default be 0. If you don't set anything, then everybody is at the same priority. And then every bridge, every port has a MAC address. And therefore, we can figure out who has the lowest ID. So taking the 48-bit MAC address and 16-bit priority makes the 64-bit ID. So everybody advertises to the neighbors that, look, my ID is so much and I am the root. Then you advertise, basically first you check it out. It is quite possible that you have a lower ID, so you could say, no, my ID is this much and I am the root. So whoever hears from a higher ID stops. At least they stop saying the root, they start saying the other guy is the root. So they might say, well, my ID is such, but I know that this ID is the root. I like to tell your neighbors and their neighbors and their neighbors. The whole network knows who is the root. Do you think it will work? The ID selection, the root selection. After they know that the root has been selected, and everybody knows that this is the root, they try to figure out what is the shortest path to that root, and that is the link that is active, and any link that is not on the shortest path is basically to the root is not active. Well, so the activity is in both sides. For example, if this one declares this to be active, then this obviously will be active from this side, from this node. So basically, with that method, so here, for example, this link is not the shortest path to the root for this node and not for this node either. So this link will be blocked. Right? And so at the end you will get a tree. And then when the packets have to be sent, they have to follow the tree. If you want to send from here to there, it will go all the way to the root and then come down. Even though there is a link here, but it is blocked. If you want to go from the leftmost to the next one, you just go up to here and come down. Okay? So the good thing about this is that everybody can come in only from one port. So for example, this port will be seen by this host only on this port here, on the top port. Because this, to come from here, you will have to go all the way here and come here, right? You cannot go from here, you cannot go from there or any other place. So there is only one input for each, actually not just for the bridge, for each node in the network. And that way we can learn where you are. So basically that's how the Ethernet learns where you are, is it just monitors all the incoming traffic. Whichever door you come in, that's the way you are located, that's the way we will send the packet out to you. Understand the source learning algorithm? Right? Some of you probably have learned this before. Source learning. I don't see any head shaking, so I don't know what is happening. Anybody remembers? Yeah.
What do you mean by the designated bridge? The minimum cost of the road becomes the designated bridge on each line.
And the minimum cost to the route becomes a designated bridge. Yeah, so basically from here you will send it to this. Actually, designated bridge will become more clearer on the next slide. So just hold on to that thought for a minute. All ports of non-designated bridges. So some bridges, actually when you have a Here in the previous picture I did not show you the real Ethernet because everything was just like point to point. In a real Ethernet you might have many bridges connected to the same wire. By the way, we don't use it anymore. But in the original Ethernet, this is where we use CSMS-CD, everybody was connected to a wire. There used to be a wire going into the roof, or not roof, ceiling, and people would just go and clamp their computer there.
Is the number is a switch, right?
Huh?
Is a switch?
These are all switches here. These are all bridges here. I haven't shown the host. Host might be hanging off too from the same wire. This is old in that sense, right? But just for the sake of that. So here what happens is that there are many bridges, and these are the MAC addresses I have put there just arbitrarily. They cannot be so simple, but I have just assumed that these are the IDs now, and all of them the same priority. In this network, what would be the route selected? Except that this should be what is next? 110. There are, oh no, sorry, this is correct. This is correct. I'm sorry, I was two networks here. So the first, this is the network actually in the beginning, and then so 101 will become the root. So this is shown again the same thing, that 101 is the root. Now 101 is the root, and so basically on this Ethernet 101 will be the designated bridge. On this Ethernet 101 will be the designated bridge. On this Ethernet 107 will be the designated bridge. Right? Because it is closest to the root. And the closest means distance in number of hops. Right? Because right now they are all same speed as well. If they were different speed, then the closeness will change. But right now this is 1 hop from the root. So this is 107 is the designated bridge, these two are not. If there is another host here that sends a packet, wants to send a packet, and for some reason it has to go through the root, then it will go to this bridge, right? So basically all the packets will be forwarded on this bridge by this host, on this Ethernet by this bridge. That is the designated bridge. Because if they go through the other bridge, they are going in the wrong direction. So that is the designated bridge concept, is that there could be many bridges on the same Ethernet, and if there are many, then one which is closest to the root will become. In the previous picture there was not such a case because every link was point to point, and so we did not show you the multi-point links. It becomes clearer here.
Bottom Ethernet, the designated bridge,
Bottom Ethernet, what would be the designated bridge? Now there are two of them, right, which are equally close, 102 and 104.
What about
105 is not connected even. Because it is blocked. You see why this is blocked? That's the one thing I wanted to explain, but let me just first. So what will happen is here there is a tie as to who can be the designated bridge, and generally tie is broken in favor of the lowest one. So 102 will become the designated bridge. Now let's see which link will be blocked here. So let's just go through this. First of all, it is very easy. Just by looking at it, you can figure out that 101 is the root. Right? I mean, of course, there is an algorithm and broadcast and everything else. We can go through that process, but at the end, it will come out, if everything is done correctly, that 101 is the root. The next thing they do is, everybody figures out, am I connected to the root? And which way I can reach the root. Right? So this one will figure out that I can get to the root from here, 105 if we figure it out from here, and so it will disconnect, and there is nobody else who will want to reach from here. Everybody else has a shorter path to the root, and this will get disconnected. This will say I'm going to disconnect it if nobody else wants it, and since nobody else wants it, 106 can get to 107 and 103 and so on and so forth. Everybody has a path to the root, so this link will get disconnected. And I think this whole Ethernet will get disconnected in that sense, is that, if there was another bridge. So right now what is going to happen is everybody is hanging off, just one hop away from the root. These are 2 hops away from the root.
I have a question.
Yeah.
The tree is automatically created by the switches
Yeah.
without any humans.
There is no human intervention required, because these links will be coming up and down. If some power fails or something happens, the link may go down, right? So we don't call the human being to come and fix it. The network takes care of it, right? This link may come up if for some reason this Ethernet goes down or this Ethernet goes down. Then this blocked link will come up. Yeah.
For your spanning tree algorithm, when you say that the connections are blocked, is that for all traffic on all ports or just for particular ports for particular services?
Okay, so that is for all data traffic. There are 2 kinds of traffic, data and control. Data is what I and you send. Control is what the switches send to each other for keeping the thing alive. So there might be some hello messages that might be being sent out. Okay, I'm connected here, I'm connected there, are you still there, is the root still there, is the root gone? All those control messages, probably some of them will be exchanged here, so that they know that the link is there. Link is there, they know, but they're not sending any data on it. Yeah.
For the switch 106, how does he know that he will block the link but below it but not the link up?
Or they just exchange the control traffic. So this one will say, I have a short path to the root. The root is 101 and you can reach it to me through at cost 1. Right? And this one will say, I have a root 101 and you can reach through me cost 1. So now, nobody wants this path, right? When you do the extra, you know the shortest path, and you will find out that there is no nobody wants that shortest path. Alright, so they will both exchange messages, control messages, saying that I am blocking this, yeah, I am blocking, and fine, done.
This is a longer path, but also we leave it open, the traffic may perhaps
Loop. Yeah, see, the whole thing is to loop, and so the shortest path with a root will never loop. That's the whole thing about the tree, is that if you have a tree and you have a shortest path, nobody taking longer path, then there is no loop. Alright, so spanning tree is clear. Clearly this has to be understood very, very well, because this is the genesis of many of the things that we will be discussing. And you can see the problems already. One of the problems is if any link breaks, let's say this Ethernet breaks, they will have to do the whole algorithm all over again, and that takes few minutes. And if your stock market, Amazon, Google is down for a minute, you know how many $1 million are going to be lost, right? And so this is not acceptable. It was acceptable when it was invented back in 1979 and 80, but in 2000 it is not. Alright, so before I go to the next, here's a simple problem. You have to just do this, which thing will be blocked and which will be the root. Alright? This homework will be due Monday. Alright, next to enhancement STP. So the problem with STP is it takes a minute, and 1 minute is too much. First of all, in 1 minute, all the TCP links will break. Alright? Because it may time out. TCP connections have a timeout and they will not hear the traffic for some time and they will break, and which is not good. So they have invented something called rapid spanning tree. And we will go through that in a minute. And then the second problem with this is that this works, it doesn't work with VLANs. VLANs we haven't talked about, so when we talk about that VLAN, we'll talk about as to what it does is. So we need many trees for VLAN, so there is something called MST, multiple spanning tree, which was done basically in 2002, 2001. And so we will see all that, right? So rapid spanning tree. So the goal of rapid spanning tree, which was again, you see, notice this little w. Little w means what? It is just an enhancement which will disappear and merge into the main standard. So this was an extension to 802.1d and merge into 2004. So D will have many versions, and if you go back and see the history, you might find like 99, 97, 2000, 2001, 4, maybe 11. So every few years they just take all the enhancements and put into the main standard. So this is an extension and this is the main standard. So today if you want to go and find it, you really want to go to 1D. Normal spanning tree takes a few minutes, which is not good. So RSTP fixes it by two different tricks. First trick is that it makes it not one periodic but also event driven. See, the thing is, STP is basically it is periodic as well as event driven. So periodic means every few seconds we want to make sure that you are alive, right? And event driven is that when I don't hear from you, I know that you are dead. And so here we do both. If something dies, and you know how we know you are dead is because even if you are not talking to me, the zeros are sent on every link all the time. All right. So if I don't hear any zeros from you, means you are dead. So either you are dead, you are not alive, or because and every 2 seconds I just check. Even in spite of that traffic, I check that you are still not only sending zeros, but you are still your brain is working too. Because you might be stuck at 0. So those two things are done: time driven and event driven. And so what happens is, once the STP is converged in the STP, in the original spanning tree, once you converge, then the BPDU is bridged PDU, bridge PDUs. PDU is, what is PDU? Protocol data unit. Okay, and bridge is the protocols. Bridge protocol data unit. This is SI term, PDU, right? So BPDUs are sent only when there is a change. Otherwise, you don't bother to tell the neighbors that my address is 1 and the route is 101, and then you can reach the route with cost of 2. You don't tell anybody that. You just did it in the beginning, and then you are done. And here, you send an hello every 2 seconds. And so that way, if something fails within 2 seconds, you will know. By the way, 2 seconds is the default. You can make it 1 second if you want. You can make it anything less than. The more smaller you make, the more control traffic you have and overhead you have. Yeah.
How does the 2 seconds come from?
Well, that is what they accepted in 2001. Right? So, see, the thing is, there is, as I said, you can make it half a second. And if you make a half a second, you'll have 4 times more hellos and less data traffic. So it's just a what we call the expert's intuition, is that there are a lot of expert people who are designing switches and everything and monitoring the traffic. They are in the standards room and they say, okay, the default is 2 seconds. Particularly when it was 60 seconds to find out. Now they can do in 2 seconds. That sounds like an order of magnitude improvement. Right? And maybe today they might even not like 2 seconds, but that is 10 years later. All right. Differentiating between the edge ports and the server. Second thing it does is it differentiates between the hosts and the switches. Now they know that the hosts have no path out anywhere except to the switch, so the hosts don't. See, the hosts have to know the spanning tree because they have to know where to send it if they have, whatever it is, right? So the host, who is the designated bridge, for example. But here, we differentiate between the edge ports and the switches, and we know that the loops are not going to be found on the edge ports, so they don't contribute to the loops. The only loops are contributed by the bridges. And we differentiate between point-to-point links and the half duplex link. Full duplex is the point-to-point, and half duplex is that shared link. CSMA CD is half duplex. All right. So we distinguish, and RSTP is used only on full duplex, which is 100% of the links these days. As I said before, CSMA CD is not used anymore, so this picture is only for teaching you guys 473, but not the real world. In the real world, the picture is more like this. Okay, everything is point to point. All right, so a rapid spanning tree will not apply if you have the old CSMA CD stuff. Obviously, if you are a bank or a Amazon or Google, you will not have it. There might be some old building left where they might still have it, but the switches are so cheap that if you haven't replaced them in 10 years, I don't know what you're doing. So so they have all been replaced. All right, so let's see how it works. Oh, the fourth. Continues, the list continues. Fourth thing it does is it merges, there were lots of states which we actually did not go into one called discarding. So previously, a port could be in disabled state, in blocking state, in listening state, and so on and so forth. And it doesn't really matter right now because we have a lot of other things to cover, so it doesn't matter. Adding 4 new flags in the BPDU. So there are new flags which allow sending a proposal and accepting or not accepting the received proposal. So now there's a negotiation. So you might say to them, look, I think we should disconnect this link. You say, no, I don't want to disconnect it. And so that is called a proposal. And so there are some bits which say, here's my proposal, and you say, well, I accept the proposal. And it is fully backward compatible with STP. If you have any STP, then RSTP is not used. So that is how it is fully compatible, is that anybody who speaks RSTP also speaks STP. But if they find a neighbor who does not speak RSTP, they say, okay, all right, you don't speak RSTP? Okay, we won't use it anymore. We'll just use STP. Okay? So let's see an example here. So here is a network. Wow, just brand new batteries. Okay. Here's the network. You see the root is connected like this. This is, you even can say this is a tree or this is a line, whatever, but there's a network. Fully connected. And suddenly this link is connected by somebody, R to A. Initially it will be blocked because, we never saw this before, but in 2 seconds we will know that there is a path. Right? Now, in the original spanning tree, we will say to the whole world, oh, new link has come up, let's just, do all the whole thing, and it will take 1 minute. In the new case, this will say, oh, I am the root, and which they already knew that this is the root, because A knew who is the root, and A knew that 3 hops away. But now it knows I have only 1 hop away from the root. So it says, oh, let's bring this up rather than the other links that I have, and I will block the other links. So it takes that link as accepted and blocks these 2 links. It basically sends the proposal to B and C and says that I am going to block these 2 links because I have a shorter path to the root. Then B and C think about it. Now B is the edge node, has nothing to do. It says, okay, all right, whatever you say, boss, I'm fine. And actually no. Basically, the B says that okay, all right, you are my only connection. I'm already going through. Previously, B was going through A, and it will continue to go through A, so that will come up. And C will find that this is a shorter path. Is it? CDA. This is 2 hops away, and this is now 2 hops away. So it's up to C to decide whether to take the shorter path or not. Right? So it is quite possible, I think as drawn here, my feeling is that C might take this, C might stay where it is, and then this link will be blocked. Okay? This link will be blocked, this link will clear, and this link, C will use this link which is also 2 hop away. Now the only difference is that if this link which is shown by the long distance has some reason to be longer than this path, then it will say, okay, I have a shorter path. So basically, C accepts and blocks CD. As shown here, C accepts the proposal and blocks CD, so then it has a 2-hop path through this path. Okay, now the whole network is basically, let's say, converged with 2 proposals, one going here and then one going here to maybe 4 to 6 seconds. Okay, RSTP. So this is rapid spanning tree. Now, multiple spanning tree is the next one, which came in 2002. Interesting. Let me see. Wait a minute. Hold on. You see, this is D, and this is Q, and that is correct. Rapid spanning tree was incorporated into D document, which is mostly for the bridging, and this is incorporated into Q document, which is mostly for VLANs. So the multiple spanning tree is required only if you have virtual LANs, and since I have not explained virtual LANs, you just basically I have to just give you a brief. This thing is that you can have many different types of traffic in the same network. So here we have 3 kinds of traffic: black, red, and green, red and blue. Okay, and everybody who is blue is here. This is very simple condition, so on. So basically, this is red switch, red network. There's a black network and there's a blue network, but this part is shared by all kinds of traffic. All right. So there will be a blue spanning tree, which route, this is the route, and it goes to these 2. There will be a red spanning tree for which this is the route and goes like that, and there is a black spanning tree which is for this is the route. So there are 3 trees here. Okay. So each tree serves a group of VLANs. It is not necessary that you have for 3 VLANs you have 3 trees. You could have 3 VLANs and just 1 tree or 2 trees. All right. So a group of VLANs are serviced by a tree, and which group is all administratively defined. So when the VLAN is defined, at that time the manager says, okay, you set up a blue. You are part of the blue VLAN, and this blue LAN will use that spanning tree and whatnot. So all that is done by administratively. But anyway, this allows you multiple spanning trees. And because of that, it could be in forwarding state for some VLANs and blocked for others. So for example, this one is blocked for red, but it is forwarding the blue and the black traffic. This is blocking what kind of color? What color? Black. Because the black tree is just like that, right? And so this is blocked for the black. So no black traffic can cross this link. And this is blocked for the blue. Yeah.
Why do we need multiple spanning trees instead of only one?
Yeah, because there are several 2 reasons. First of all, not all VLANs go all places. Even though you have one network, red VLAN cannot come into this building. It is president's building, very secure and things like that. Okay, so not all VLANs go to all places. So that is one simple reason, that you don't want to basically use the same route and same everything. Each VLAN is basically complete in itself. They don't know actually. The VLANs guys don't know that they are sharing anything with anybody. So they have their own spanning tree. Although, as I said, they could be sharing a spanning tree too. Like, you know, each spanning tree serves multiple VLANs. Okay? Any other question? Yeah.
So is the VLAN could be over the IP, right? IP3?
No. There is no IP so far, and I want, in this whole lecture, I will not use the word IP. This is data center Ethernet.
So, but I heard that the VXLAN is this could be.
I haven't talked about VXLAN. This is VLAN. We'll talk about VXLAN when the time comes. That is actually 2 or 3 lectures away. So basically, right now we are at layer 2 and we are not talking anything about layer 3. The only relationship is that the LAN traffic does not go through the router, right? You know that. The LAN broadcasts do not go through the router. So the VLANs cannot be passing through a router. I mean, if the LANs stop on a router, the VLANs will stop on a router. Go ahead.
I mean, in the data center, I heard that. So even because VLAN has only 4K, right? It's a limited 4K.
Okay, yeah, a little bit ahead. So I'm going to come to that part when we come. So there is a lecture which is actually 2 or 3 lectures away where we talk about extensions to Ethernet for data center. Okay, extensions to Ethernet for data centers. That is where we talk about all that. Yeah, but yeah, so you're right. But right now, I'm sorry, what was the question?
There's no question on it, just that because in the data center they're trying to using a
Lot of VLANs. Okay, so the point was this. Let me just make the point right now. I haven't talked about VLANs, but I think that is the next thing. It's coming up in a minute, VLANs. So the maximum VLANs allowed by the first standard, which is 2005. Well, 2005 may be the second one, I don't know, second revision. But by 2005 or so, they allowed only 4,012, 4,098, 95 actually to be exact, 4,095 VLANs. And that is not enough in a data center. So they have new extensions which allow more. Yeah, okay, yeah.
But VXLAN is not on the same layer as VLAN. It's above IP. It runs on top of IP.
So yeah, I think we are talking about something that we haven't even talked about the rest of the class. So I think let's keep that step.
VXLAN is not in the same
Yeah,
layer.
okay, yeah. All right. Now I'm going to talk about a protocol IS to IS, which is not even a TCP/IP protocol. It's a OSI protocol, which you have not been taught, I guarantee, in 473. But it's very similar to OSPF, except that this is not a TCP/IP. TCP/IP uses OSPF. OSI uses, actually was hoping to use IS to IS. So it was designed very generally, and therefore it is used at many places. IS to IS is used very many places. It's like OSPF. The main difference is it is not dependent upon IP. It does not require IP addresses. You can use any address. You can use IPv6 address, v4 address, MAC address, any address in the address field to exchange. So that's the strength of it. It's a general purpose route table making protocol. OSPF is a routing protocol, right? It makes a routing table. IS to IS is more general than OSPF because it can make the same routing table but for any other addressing that you're using. All right? And IS stands for intermediate system. And what is an intermediate system? That's what we call router in the TCP/IP world. In the OSI world, there are 2 kinds of systems. Intermediate and ES is the exterior system, exterior and interior. ES. Okay. So basically there is a end systems and the interior systems, right? The edge systems or whatever. So basically interior systems is same thing as a router or anything. So here I think this is also a general term than router. Even the switches are intermediate systems, right? Switches are going to use this in a minute. IS to IS. So IS to IS is intermediate system to intermediate system protocol to build routing tables. It's a link state routing protocol. So now, this is where your 473 comes into practice. Does anybody know what is the opposite of link state? Or what is the alternative to link state? Does anybody know what is link state? So how many of you took 473 here in WashU? Nobody? I wonder what they teach in the networking course. Alright, there are two kinds of routing protocol, link state and distance vector. In the link state, what you do is you tell your connection. You took it here 473. Not 473. Okay. So the idea is that there are two kinds of ways of finding your route, or finding the whole graph of the network and finding the shortest path and all that. Is that you tell the whole world about your connectivity. So I tell that I have two connections, but I tell everybody. I send 19 messages, one to him, one to him, one to him, one to him. The whole world I say that I have two connections. Or I tell to my neighbors only, but I tell the distance to everybody. So I say, well, I have 1 hop from him, 2 hop from him, 3 hop from him, 4 hop from him. So that's the distance vector. It says long vector because there could be 2,000 of you. But I tell you only 2 people. Right? So distance vector, and those are the two methods of telling the whole world where I am. Right? And then the whole world can then calculate. So link state is better actually, and that is used by OSPF. Before OSPF was a protocol which I forget the name. What was it? Routing protocol, RP something. Anyway, so that was distance vector, and that had its problem. Anyway, so OSPF is link state, and link state is what we use everywhere. IS to IS also uses link state. So that means end nodes send its connectivity. Actually, I should not end node. Each node sends its connectivity. That means the link state to all the nodes in the network. Okay. Then they use Dijkstra's algorithm. Everybody knows what is Dijkstra's algorithm, right? That one they teach, right, in every place, I hope. If not, then you have to look it up, because then I would be going back to 473, if nothing else. So Dijkstra's algorithm to find the routing table. It is similar to OSPF. OSPF is designed for IPv4 and then extended for IPv6. IS to IS is designed. It can be used with IPv6 without any extension. It can be used with IPv4 without any extension. We are going to use it here for Ethernet without any extension. Alright? OSPF is designed to run on the top of IP. IS general, it can run on anything. So it can be, that's why it was adopted by the IEEE people. So now what we use is what we call shortest path bridging. 2012. Obviously this is not in the books, but it is in practice, it is being used. So shortest path bridging is basically all the switches exchange the link vector and find out what is the shortest path to go from server 1 to server 4, or from anywhere to anywhere, right? So they will figure it out. If I want to go to server 2, all I have to do is go to switch like that. If I want to go to something, I have to go this way and that way, and not. So basically, that is the shortest path. So now all the links are used. You don't block any links. Okay, and that way it is called better CapEx. What is CapEx? So the people who manage these data centers, they have two kinds of expenses: capital expenses and operational expenses. Operational expenses are things which you have to do day by day. Capital expenses are things that you buy and then you just gone. Right? Operational expenses are including the operator and electricity and things like that, right? And the CapEx is buying the equipment, power supply, generator, those are all CapEx. Running the generator, you need the oil, that is OpEx, right? So OpEx and CapEx. So this is better CapEx. Because once you bought the link, 100 megabit, 1 gigabit, 100 gigabit, whatever, you want to use it, right? You don't want to block it. So this is the one. IS to IS protocol is used to find the shortest path, and if there are multiple paths with the same distance, both of them are used with equal cost multipath. So basically, you hash and you decide, randomize, and you decide as to how to get there. There are two paths here. From server 1 to server 4, you can go by the red path, or you can go by the blue path. Right? And you will use both. Half of the packet. Not that you will send first packet here, second packet there, because that would really cause confusion. Because if the links are not the same distance or same congestion, some packets will arrive out of order. So you hash so that all the packets which have certain thing in the header will follow one path. Other packets which have something different things in the header will follow other path. All right, it might be the IP address, and so you just hash on little bit longer than into the packet. Equal cost multipath is used. So now you are using all the capacity. You bought two adapters. You bought for two links. You are going to use both the links. Yeah.
Does this protocol tries to make sure that every two paths has no common links?
Every two
paths has no common links. But it has
Every two path.
For example, the red path and the blue path, they might have no common links.
Oh, basically, red path and blue path, they have no common links. See, what happens is, what this switch knows is that I am 2 hop away from server 4 on red path, and I am 2 hop away from server 4 on the blue path. It will decide between the two of them and then send it here. Now this switch will then decide how many hop away I am from here to there. If there is a common link, then it doesn't have to make that decision. If it has two different paths, then it will decide that I want to send it here or there. So although I have shown you the red path here, this is not something that this switch controls. This switch only knows that I have two alternatives here to begin. It's just one hop decision.
So it's still possible that two paths may share the same link.
If there is only one link, yeah. Say, let's say this blue link is down. By the time it will figure it out that there is no, the path is not shortest path, because this IS to IS will figure it out. You know the complete. Basically, the idea of IS to IS is OSPF or anything is that you have the complete graph. Every node has a complete graph of the network, so they can figure it out, right? That there is only one link here, and so on and so forth. And even if there is a common link, that's not bad, because if you have two paths, let's say you want to go from here to California, but you have two paths up to Kansas City, and from Kansas City you have only one path. It's still better that half people go through this path and half people go through this path to Kansas City. From there is no choice. Or let's say you have one path from here to Kansas City, but there are two paths from Kansas City to California. It's still better to take those two paths and use them. Right? So it's okay. Yeah.
So is there a disadvantage for this protocol over the Spanish book?
I'm sorry?
Is there a disadvantage in this protocol?
Is there a disadvantage to this protocol? Well, this is just a lot more work, I would say, at this point, first of all. Second is that it is new, so not all the switches may know. If some switches don't know, then you are in trouble. You have to fall back to your old system, which everybody knows. Right? If suppose you don't speak IS to IS, then I can't really make a whole graph. You won't tell me that my distance, to who am I, right? Things like that, right? So basically, that is the thing. Is this is new, and everybody has to speak it. It's more complex. What else can I say? And the second thing is, it is only 2012, so we will know the problems in 2014 when we have something else, SPP version 2. Right now, this is too early to say anything negative. See, the original Ethernet, when it was designed with the KISS principle. Everybody understands KISS principle? KISS? Keep it simple, stupid. Right? And STP was that. spanning tree was that. It was not optimal. It was not optimal. We knew that, but it was simple, and so that was fine. Now people are saying, no. We cannot be so stupid that we put a 100 gigabit link and not use it. So we are just, getting rid of the last S as much, because but the first S becomes a little bit complex. All right, move on. So now we go to virtual LANs. But before I go to virtual LAN, I want to make sure that you all understand what is a LAN. Okay, so the definition is not by the distance, not by 2 kilometers, not by 5 kilometers, not by 200 meters. The name local is misleading. A LAN is a single broadcast domain. That's the definition of a LAN. If I can hear your broadcast, we are in the same LAN, period. I could be in Germany, but if I can hear your layer 2, we are talking layer 2 broadcast. If I can hear your layer 2 broadcast, we are in the same layer 2 domain, layer 2 LAN. We are layer 2 network, which is a LAN. And in the IP terminology, we call it a subnet because the Ethernet broadcast cannot cross the subnet. A router will not pass anything which is not addressed to a unicast something. So therefore, in the IP world, it is a single subnet, and so there is no, when you talk to other members in the same LAN, you basically don't need routers, right? You can just send an Ethernet packet and it will be picked up by the other guy or forwarded by the bridge all the way to the other guy, and so you are much faster. Going through router is kind of complex. So, but if you go to other LAN, then you need the IP, you need the IP address, you need the router, and so on and so forth between the two LANs. So here you have a LAN 1, you have a LAN 2, you need a route. You have a router, that means this people will broadcast, but these people will not hear those broadcasts, right? Here, these two people are on the same LAN because they are connected by a bridge. When somebody broadcasts here, they will be here. Broadcasts are forwarded by the bridge. What does bridge does not forward? There is something that bridge does not forward. There was another domain we had talked about in the last class. Hubs. What kind of domain they make? Yeah. So the bridges don't forward a half packet or incomplete frame or anything like that. All right, but hubs do. Right? They don't wait. Hubs don't wait for the end of the frame. They just start sending the first bit in, first bit out, and so they can cause collisions. But in the bridges, on one side and the people on the other side, they don't collide. So people can speak here happily on this thing, and they can speak happily on this thing at the same time. They will not collide because only the full frames will be forwarded. But they can still have basically, but still this is one domain because it is broadcast domain. The broadcast packets will be fully sent from here to there. So there is one broadcast domain. By the way, you got to keep reading every day when I give you the reading assignment. So this was in the previous reading assignment. I think it was maybe, or maybe not, I don't remember. But this whole thing about the bridges and the switches and routers and hubs we discussed in the last class, and I have a reading list at the end, maybe in this same module, but you got to keep up because we are going to use it one by one, and that's why the slides are in that order, because once I tell you something, I need to use it next. So anyway, so a LAN is a single broadcast domain. Agreed? So far? Okay. So what if we have three departments: marketing, engineering, and manufacturing. Obviously, marketing does not want engineering to see its data. Manufacturing does not want. Actually, marketing, engineering, and manufacturing are not that don't have that enmity. But if it was finance, they don't want anybody to see their packets. Finance people in any company are very, very, closed department. You don't know what is your president's salary, and they don't want you to see that either. All right. So the finance. So how do these people do? They have to have a separate network. Well, even if they have separate network, what if the finance guy moved from second floor to the first floor because there was not an office left there? Now we need a separate network from the first floor. So the idea is a company will have one network, but somehow we have to carve out virtual networks out of this one physical network. Right? So we will have, in this case, we have this network and we want to carve out 3 different networks: marketing LAN, engineering LAN, and manufacturing LAN. Okay? If you ever want to cross from one LAN to the other, you have to go through the router. Okay? And you cannot directly broadcast or go or see or anything like that from other LANs, even though you are on the same fiber, same copper wire, same switches. Okay? So we need to do that. That is a virtual LAN. So basically, you can think of this. You can, in your company, you have many different colors of the hosts, not the bridges. The hosts are different colors, and all the hosts of one color are on one LAN. All the hosts of different color are on different LAN. So basically, you have this engineering department, which is red color, finance department is blue, and so on and so forth. And so when you come in, you sign up your sign-up paper and say where you are signing up finance department. Your computer is put into the database as you belong to the red host, red LAN, red VLAN to be exact. All right. Now your computer will see only red broadcast packets. It will not see blue and green. So they went through several processes, and finally, basically, so all of this is history actually. First they thought that layer 1 would be the right thing, that each port will be declared as a LAN, as a VLAN. So for example, we could say the port A1 is in VLAN 1, port A2 is in VLAN 2, port A3 is in VLAN 1, port B1. So here's the thing, you have these switches, and we could just go port by port, and these are the end hosts, by the way. So these ports, we could say this is marketing, this is engineering, and so on and so forth. But this is too much work. Why too much work? Because somebody has to watch every day whether the marketing guy is moved or not, he's still there or not, right? It's just too much. So then they said, we will do MAC addresses. So we will note down your computer address and then write it down in a table someplace that this MAC address belongs to marketing department. And that went on for some time, but I think finally ended up with layer 3 VLANs. A layer 3 VLAN simply means that, when you go to get the IP address, when you go to the DHCP server or you a static IP, whatever it is, basically whatever subnet you are in, you are given, that decides which VLAN you are in. So basically you say, well, I am Raj Jain. Then they say, oh, you are in the educational department, something like that, as opposed to finance department. And so you get a subnet address, or you get an IP address in education subnet. In our case, we'll get a CSE subnet. And we won't be able to see any finance data. Right? So basically, everybody who has this IP address, now here is where the Ethernet and IP get mixed up in this case, is that if you don't have an IP address, you don't get a subnet, and then you don't get a VLAN, and then you can't do anything. But the idea is that is the easiest to manage for the people who are managing these networks. They can just manage it through their DHCP server through some rules. All right? But it is equally actually as good as this one here, second one, because what they are doing is in the DHCP server, they are looking at your MAC address and then giving you IP address. Right? So there is some table somewhere. Anyway, so what happens in the packets? How does the switches know who is in what LAN? So each packet now has something else in the packet. Actually we don't call it packet, by the way. We call it frame. So just to be exact, layer 2 things are frames. Layer 3 things are datagrams in IP world. Okay? and layer 4 things are something else. So every layer has a name for it, okay? And so layer 2 is frame. In the OSI world, we would call it layer 2 PDU, protocol data unit, layer 2 protocol data unit, layer 3 protocol data unit. But in the IP world, we don't use layers and actually in that sense. So basically, we have a name. Frames are for Ethernet. Datagrams are for IP. All right, so a frame, untagged frame. The original frame was like this: destination address, source address, type or length field, then the data field, and then the CRC. Now here, if the type was LLC, then you will see LLC header. And so this is the original frame. Now with 802.1q, we add 32 bits. The first 32 bit is the protocol type. So this is TPI. So this indicates what type of header is next. And this will say I have a VLAN header. So this is fixed for the VLAN type. Okay. There is a particular bit pattern which you can find in Wikipedia and other places. I didn't want to put it here because it's not relevant and you will unnecessarily kind of trying to remember what is the TPI for VLAN. So there is a TPI for VLAN. So this one says everything that follows is VLAN header. And then the real protocol type is here. So once you are finished with VLAN, then you say, what do I do with this frame? You look at the type and length field, and this says, oh, this is an IP packet. So the original type and length field is sent here. We put a new type length field, and that is VLAN. Now, so out of these 32, 16 bits are gone. Right? We are left with the next 16. 3 bits are for priority. 1 bit is for CFI and DEI, and 12 bits are for VLAN ID, what VLAN number you are in. Okay? Now, what is CFI? In those days, there were something called token rings. We don't have token rings anymore, by the way. All right? In those days, there were token rings, and the token rings used a address numbering system which was slightly different than the Ethernets. The order was different. One might send out the first bit, the most significant bit first, the other might send out most least significant bit first, things like that. I don't remember exactly. So there is a canonical format which is for Ethernet standard format, which is 0. CFI is 0 means it is standard format. If it is 1 means it is token ring format, because there was a case also where you could have token ring bridged into Ethernet, because both of them are 802 frames. You might want to send them over Ethernet sometime. So CFI indicates whether this is canonical or not. Now there are no token rings, so we don't need CFI. So now it is used for DEI, drop eligibility indicator. That means this packet has a lower priority or high priority. If you get into trouble, throw this packet away. All right, 0 means good, 1 means no good. All right, so that is 1 bit. Now we have 3 bits priority. So the priority means we have 8 priorities, 0 through 7, and 7 is high. 7 is high means if there is a trouble, 7 gets through, 0 is dropped. Of the packet? Oh, actually, basically the source does. So the source wants to send a lot of traffic and then puts some 0 and some at 1 and so on and so forth, because here you think, suppose you are doing video, the video generally has E frame, I frame, not E, I, P and B frame. There are some frames which are a higher priority for you. You want to make sure that if there is a congestion, please don't throw away my I frames, throw away my B frames. So you mark them lower priority and higher priority. The network doesn't.
So application layer determines.
Yeah. If you are doing a backup or something, it's not very high priority, you can mark it low priority. All right. So there is a priority, 8 priorities, 0 through 7. 7 is high, 0 is low. And so that is part of this VLAN. And this is the reason I have to put this part of the lecture in this module, I really didn't want to get into virtualization at this point, but I need priorities. Since I need priorities, I needed to explain this whole 802.1q. All right, we have a whole virtualization coming up in a later lecture. So anyway, so now that we have priorities, so now we understand that we have 8 priorities in Ethernet, and they are in this VLAN tag someplace. And so every packet carries this, and when a bridge sees this packet is coming from this VLAN ID, so whether it should go here or not, whether it should go there or not, and even the broadcast packets have the VLAN ID, so it can decide whether this broadcast should go on this side or not, whether this broadcast should. All the broadcasts are sent to everybody on the LAN, right? So that means all the broadcasts are sent to everybody on that VLAN. So the marketing people's broadcast will not be seen by the finance people. In fact, marketing people's packets will not be seen by the finance people either, the unicast as well. All the packets will have VLAN ID. Okay? So now the forwarding is done on the basis of 2 things, not one thing. Previously, it was done basis of the destination address. All the switches did was look at the destination address. They don't look at source address. They just look at the destination address, where are you going, and they say, okay, go through that door. Now they look at 2 things. What are the 2 things? VLAN ID is first thing. If you say I am VLAN ID and I want to go to the marketing department, they say, oh, sorry, that door is closed. You go to the router. You know. And so you cannot go to certain destination on that VLAN. Your packet will be actually dropped. I mean, you won't get any message saying that it goes to the router. It will be just dropped, and so the destination not reachable kind of message you will get. All right. So those are 2 things. Now, moving on. So the next protocol is LLDP. Now, Ethernet has all so many options and features and so on and so forth. So they needed a protocol to manage all this automatically. So you can ask a switch, do you implement RSTP? Do you do link aggregation? Do you do VLANs? Things like that, right? So how do you do it? There is a protocol for that, and that is called LLDP, Link Layer Discovery Protocol. So it is actually what they call neighbor discovery. What that means is that you can ask your neighbors, what can you do? What are your capabilities? Right? And that is what neighbor discovery is. First of all, finding that, yeah, there is a neighbor, and then second, finding out what they can do. Right? So that we do the right thing. So this is a neighbor discovery protocol by periodic advertisements. Every minute, an LLC frame is sent on every port to neighbor. What is LLC? Yeah, logical link control. It was said in the last class, I think. In the last class I talked about it, right? That 802.3 introduced logical link control. LLC frame is sent on every port to neighbors, and the LLDP frame contains information. It's just a very general frame. It can have any number of fields. Each field has a TLV. TLV means type, length, and value. So here is the LLDP frame: destination address, source address, length of the. This is actually T/L. It should be type/length. Oh, basically length, because I am showing LLC. This is an LLC frame. So basically, it will have a length field. In the LLC, it will have all that information, and which I am not showing here. But anyway, after LLC, you have TLV, 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 as many TLVs as you want. So what is type, length, and value? Everybody understands what is TLV means? Is that when you submit something, you say, well, this is information is number 13, and its length is 2 bytes, and value is 15. Now, what is number 13? Everybody knows what is number 13 because there is a standard for that as to what type 1 is, what type 2 is, what type 3 is, what type 13 is.
So that means every value comes with the length.
Every value comes with a length. Now the question is, if you knew the type, then why do you need the length? It's type 13, right? But the answer is sometimes some fields are variable length. For example, my name is only 7 characters. Your name is 25 characters. So we need to put a length field.
flexible. That's why.
Yeah. Type, length, and value. Type is what information it is. Length is what is the length of this information, and value of this information is V, right? So TLV encoding. So basically, so there are many types which have been standardized, and there are many types which are being standardized, and every time some new protocol comes up, a new type comes up. Okay? So here's my chassis ID, my port ID, time to live, port, a descriptor, who made me, what is my product name. So you could say, well, I'm Cisco 2305, whatever number that is. And so basically this is useful because the other switch can use it, or the manager can use it for that information that, this is my inventory right now, and this is the capability. And system name, capabilities, MAC address, IP address, power by MDI. What is power by MDI? First of all, what is MDI? MDI is media dependent interface. So basically, the Ethernet originally did not carry power. If you connect two devices with Ethernet, both of them have to have power. But they noticed from USB carries power. Right? So in USB devices, you don't need power. You can just connect a device and it works because it's getting power from the computer. So they said this is really good. So now Ethernet provides power. So, but not every computer or not every Ethernet interface, particularly the ones which are old, provided. New ones do, but old ones don't. And you need a lot of power in some devices, so on and so forth. So there is a whole mixture. So anyway, so that is a capability that some switches have or some ports have, power by MDI. Okay, this is actually not so prevalent today still that anybody will depend upon that. So really every device that can be powered by Ethernet also has a power port. So because it is not prevalent right now. You haven't heard about it so far, I suppose. So obviously you know. But there are cameras, particularly security cameras nowadays have to be connected everywhere, and so they can connect to the Ethernet and then they don't need power. As long as they have Ethernet, they're done. But your switch has to have power. And it has to supply power on the Ethernet port. Alright, link aggregation, maximum frame size, everything else. By the way, maximum frame size went into the drain already, because if you had a 1518 byte frame and you added 4 byte, it became 1522. You guys at the end. Hello? Can you close that computer? Somehow it bothers me. I'm not sure whether you're paying attention, full attention here. So please pay attention. So anyway, so the idea is that now the question was last time in the quiz that maximum frame size 1518, that was someday. It no longer is. In fact, as we are adding more and more protocols, the length is becoming longer and longer. Well, I mean, I think it depends upon the day. I mean, if I tell you some answer today, I won't be right tomorrow, so I haven't kept track of it. All right, but somewhere around 2000 or 1800 or something, so the thing is, numbers are, kind of variable depending upon whatever it is. But anyway, so all that has to be exchanged. We exchange what is the maximum frame size, yeah.
In terms of this protocol, you could have switches or routers in different subnets or even VLANs. In order for this to be effective, would you need like some type of VLAN trunking, something like that?
VLAN trunking. I'm sorry, what do you mean?
To be able to communicate across VLANs to your different switches and routers in their own, broadcast.
Okay, so if you want to connect two VLANs, as I said, you need a router. And I did not say this in this picture, but you see there is a router here which has only one port. Okay? The reason you need this router is because if you want to go from one VLAN to the other, you need to go to the router and you can come back on the same port, but you are on a different VLAN now. So if that is what you mean, yeah. So there are routers that you can cross from one LAN to other LAN or from one VLAN to another VLAN. Alright, so now you understand LLDP. Alright. So now I can get into some new protocols which are called data center bridging protocols. Now still I am not going to talk about the virtualization, but there are several protocols that have been done very recently, and you can see the dates here. 2010 and 2011, these protocols have been done specifically for data center bridging. 4 of them. And actually, these are mostly for storage traffic. Storage traffic has one characteristic, which is that you cannot drop it. If you drop it, it is really bad. If you read a disk and you get a read error, you get worried. Right? So we are not used to seeing read errors or write errors or any disk errors. The day I get a read error, I start thinking of changing the disk, basically buying a new disk, which is a few $100 thing, right? So the idea is that we are not used to just getting an error like that in the storage. On the network, we get the error every day. I mean, every day I get packet lost, too delayed, something, congested, can't reach the host. That is every minute thing, right? But on the disk storage, we don't do that. So they had to change Ethernet so that it doesn't lose any packets, actually to be exact frames.
So
Yeah.
losing packet actually depends on the transport layer.
The losing packet depends upon transport layer, you mean the TCP?
Yeah, the TCP or UDP.
Yeah, so the thing is, TCP is not good enough for data center. First of all, in data center, we don't even want to go to TCP. We don't even want to go to IP. Right? So I want to be able to read my disk using plain Ethernet. Okay? Now, and there are cases, we have a module on storage by itself where we will talk about, you need IP, but in many cases you really don't want to go higher layer. Right now, when you read your disk, you don't go through any protocol. You just have a SCSI in your computer and you just connect it like that, right? There is no protocol, no IP, no TCP. I mean, you read your disk, right? I mean, like that. And so that's what we want to kind of keep is in the data centers. Actually, I'm sorry that I don't want to go into storage right now because we have this data center bridging to discuss. And storage is the next module, which is where we'll talk about fiber channel, which is what you don't use at home, but fiber channel is what is used in the data centers. And it has certain things. And one of the things it has is it doesn't lose packets. So anyway, 4 standards: priority-based flow control, enhanced transmission, congestion control, and data center bridging exchange. And I'm going to just go one by one. So flow control is easy. Basically, in the old days, Ethernet had a frame called page frame. When a switch sent a page frame to somebody else, that switch basically blocked that port. Means it will not send any more traffic on that port until that page expired, or it got that okay, something like that. Basically, page has a time field which says please don't send me anything for 1 second. If I send you a page frame which says please don't send me anything for 0 second, that means you can send. All right, that means don't pause anymore. So the same page frame basically will come back, or it will say time may expire, one of the two. Until then, you don't send anything because it will be dropped. It was defined in 1997. This is what we call on-off flow control. You can turn on the flow, you can turn off the flow. And the frame actually just a little bit detailed. That is not a unicast frame. You just don't tell the neighbor. You just send a broadcast frame, so you don't really have time to figure out who your neighbor is. You just send it to this address, and since it's a multicast address, anybody who listens to that multicast address will work on it. The another new thing about this is that this is not forwarded. So this page frame, even though it is a multicast frame, it is not forwarded. All the multicast frames are forwarded. But the main problem is it stops all traffic, and therefore very soon this will back up. Its buffer will fill up, and it will have to tell the other guys, please stop, and they will tell the other guys, they will stop other guys. So congestion is in Kansas City, but all the traffic in St. Louis is congested now. Why? Because there is back pressure. Okay, so there are two problems. One is the back pressure, second is that all traffic. So they fixed it. They fixed it by putting priority-based flow control. So now each priority can be stopped individually. So you have priority 0, 1, 2, 3, 7. You can say, please don't send me anything priority 1. Now the priority is not really a priority. You might be able to send 0 but not 1. Now 1 is higher priority, right? But no longer. Now priority is just like a class. Don't send me anything with that bit being equal to 1. That's 3 bits. Right? So you can individually block any priority you want. Priority 1 blocking does not mean the priority 0 will stop. So if you want to block all priorities, you just block all. If you want to try everything up to 4, just send 4 frames, 0, 1, 2, 3, 4. Priority based flow control. That's all there is. Alright, and obviously the pause frame as before has a time to live, and so up to that time you don't send. After that you can send, or if you get another pause with the 0 time to live, you can send. Is this protocol clear? Alright, so one thing is, with this, at least a high priority can continue, the low priority can back up or can be dropped, if you want to call it that way. It's up to you to decide what can continue or what should be dropped. The next thing is enhanced transmission selection. Second thing, there were no guarantees before, and people wanted guarantees for the storage traffic. They wanted to say that, well, I want to make sure that I have 75 megabit available for storage, otherwise my storage is will not work. So they created that by enhanced transmission selection. Here, what we do is you take these. Now we don't call them priority. We have classes 0 through 7. And then you can group them. So you can say group 1 is these classes, group 2 is this classes, and group 3 is this classes. And so the classes are what is marked in the frame, and the group is what we want to manage. So we just want to manage 3 groups or maybe 2 groups, maybe 5 groups. I don't know. It doesn't matter. The number doesn't matter. But really, you group them, and then you say, I want to have at least, out of my gigabit, I want to have at least, let's say, gigabit. So I want to have at least 100 megabit for group 1, or maybe 500 megabit for group 1. Okay, and I want to have minimum of 10 megabit for the group 2, and I want to have minimum of 10 megabit for group 3. So you can allocate some guarantees bandwidth, except the rule is that you cannot allocate more than 75%. So the 25% has to be left for the best effort, for something that is not reserved. Up to 75% can be guaranteed, can be allocated to be exact. And the second rule is that if somebody doesn't use their allocation, other people can use it still. So if I say, well, I want to have my 500 megabit for group 1, but there is no group 1 packet in my queue, group 2 and 3 can go. Alright, so nothing is wasted. Alright, with those 2 rules, the rules are traffic is divided into classes are grouped, then the fairness within a group. So now here is an example that if you have a group and there are some queue here, there is some queue here, there is some queue here, there is a fairness, round robin. So you don't want to send all the packets of one queue in that group. Okay, now fairness is itself a lecture and I would not go through that. So there is something called, I forgot the name. What is the fairness from Berkeley or Stanford? Fair, maximum fair? No, not maximum. It was bit by bit fair, that is called when you have bit by bit fairness. Anyway, so the fairness has many ways. Okay, fairness could be, maximum fairness is one example, but there are many other ways of fairness. So I would not go into that one. But so you will be fair among these 3 queues, and this will be fair among those 2 queues. So fairness within a group, 3 to 8 classes, and at least 3 classes generally are recommended. So one is with PFC. So one is the class with PFC, which is the priority based flow control, and one without the PFC, and one is strict priority. So they would have 3 groups. This one will have strict priority. This one will have the one with PFC, without PFC, whatever. But basically, you can make as many classes as you want. This is just sample. And bandwidth is allocated per class group, and bandwidth unused by a group is used by others. So here is an example. So suppose we have 3 groups, and we say group 3 gets 3 units, and group 2 gets 5 units. So here's an example. Group 3 gets 3 units, group 2 gets 5 units, and group 1 gets no reservation, right? And let's say they send 2, 2, 2, 1. If they send 2, 2, 1, they will all get through 2, 2, 1 because everybody is sending below their reservation, and there is nobody else to use the leftover anyway. But if they send 3, 5, and 3, so this will, group 3 has 3, so they will get 3. This one has 5 to send, but its reservation is 5, so it will get through. And this one sends 3, this will only get 2 because total is 10. So 3 plus 5, 8 plus 2, 10. The whole link is used. So they will, even though they send 3, they will get only 2 because that fills up the capacity. Now let's take the third example, third second. They send 4, 6, and 2. So 4 will get 3, guaranteed. 6 will get 5, right? So now there is 2 and 1, right? So basically this one gets 2. Actually this is already overloaded. So basically they get 2 and these get their capacity maximum. Okay? Actually it would be better if I had another example here, which I will add later on, where these two don't use their resources and the link is not overloaded, then they can get something more than their reservation. So for example, this should be able to get more than 5. We don't have an example here. But they would get more than 5 if, let's say, the first group was not using anything. Right? So that is the thing, is that anything not used by everybody,